Now we are going to break that law. So we take this over 1, a very simple step function that we use. Again on the interval 0 to 3. And we choose fx to be 0 on the interval this is equal to 1 for x belonging to 1, 2 and equal to 2 for the interval x belonging to this is the open closed interval. That means at 2 it is defined from here. At 1 it is defined from here. And so on. So let us mark it. Let us draw the graph. So this is 1 including this point. So this is 1. This is 2. So this is equal to the graph is 1 here. And at 2 is 0, 1. If you compute AX, the area function, this turns out to be 0 x minus 1, 1 to 2. This is equal to okay. It's simple calculation. Compute everything with x chosen between 0 and 1, x chosen between 1 to 2, x chosen between 2 to 3, and I think almost in your mind you can, you don't have to take your pen to compute this. Now you observe that in this case also a dash x equal to 4. Now there is a problem. Come to this problem. The function is not differentiable at the point 1 and 2. So this is going to be on the interval. So except that is on the interval for x belonging to 0, 3. Let's look at this. And if you plot the graph of this function, it is going to be the following. So it is going to be linear on this part. And then on this part, it's again linear. And then on this part, it's again linear. And this is where the function is given by 2x minus 3. So that at 2 it is passes through the point 2, 1. And at 3 it passes through the point 3, 3. Now clearly you see that at 1 it is a bend. And so also it is a bend at 2. Although the function is continuous, a is continuous here, but f is not continuous. Therefore, one more inference that you make is that when you go to calculate the area function, you get a, even from a step function, you end up with a continuous function. Or in other words, computing the area function will just smoothen the function more than what we have originally started. So except at the discontinuity of f, we have a as the antiderivative. These two examples are important, especially this one, the one that we are looking at is important. But now, once again, you go through the computation. So compute and verify the following. That is A, this is equal to so in all these cases this particular rule formula works. What is this AX? AX is essentially the area between this we usually denote by the integral a to x ft. What you get this is we have not proved it or anything, but we can at the moment symbolically write this as right. So this is the general formula that evolves, and this you would have seen somewhere in your calculus where you talk about what is called the fundamental theorem of calculus. Okay, so we do the following that if this is a fundamental theorem. And there are some conditions. This is a very crude way of putting it. This is what is called the fundamental theorem of calculus. So in all these, we have computed the antiderivative without using any integration. And we observe that it is the so-called area function which turns out to be the antiderivative. And you know that this area function is essentially what we designate with the integral. Therefore, this connects them up, the two ideas. One is a geometric idea, the other one is purely sort of algebraic relationship between the function and its antiderivative. You know the definition of the antiderivative, it is a function whose derivative is a given function. Okay. That's it. Now let me consider a fifth example. It's a very simple example. I take fx to be equal to -1 on the given. What is the graph of the function? Now you see the graph goes below. So this is the graph of the function. We calculate the area function. Now, when you calculate the area function, first of all, we have to be clear what exactly you mean by that. Again, as we worked before, and this is the area of this rectangle. Area is a measurement. You want this to be negative? Normally, you say that it is positive, so therefore, you will simply say that it is after all x, because it is the distance x multiplied by the length of this line segment, and that's equal to 1, and therefore it is x. But if you do that, I mean, let us take the scenario that this is equal to x. In that case, what is your a derivative of x? A derivative of x in that case is 1. You don't get back to your end. So it is inconsistent with the antiderivative concept. The area function do not give the antiderivative anymore if you were to assume the area is not negative. Suppose you define, change the definition. Take ax x into minus 1. This is minus. In that case, you observe that a derivative of x equal to here. Therefore, we designate whenever we have a function and its graph, we designate the following. If you have a function something, now what is the area enclosed between the curve y equal to? It is the sum of the area of this plus this plus this. But what is this? This area is negative and these two areas are positive. That means wherever the graph of the function is above the x-axis, then the corresponding area is considered to be positive. Wherever the segment, the function is negative, okay, then that is the graph of the function is below the x-axis, then you take the area enclosed to be negative. Okay, that is the moral of the story, that by considering this. In that case, one can get possibly a derivative equal to fx. So the area of function will simply give you the what is called the antiderivative. Okay, so with this convention, another example where you have 1, 2, 3. We take the function to be minus 1 on this interval and 1 on the interval 0 to 2. So there is a step function which is actually, so this is equal to 1. So we take fx to be equal to minus 1. This is equal to 1. Now for this function you compute the area. If you compute the area, now you see that here, see that the area function or area segments, you have to compute it separately. So this part is going to be given by minus x for x belonging to, from 1 to 3, what is that? It should be equal to, okay, let us compute this. So somewhere here, so this here is going to be, this x is here, this is going to be x minus 1 into 1, so x minus 1 minus 1. So this is going to be, it's minus 2 for x belonging to 1 to 3. So how does A look like? This is the area function. The area function takes up the following form. We go for the graph of area function. 1, 2, 3. Now you see that the area function takes the value minus 1 here, so it is this length segment, and then 2 vanishes, and then this 2 segment. This is the area function. So this is the area function that we have. So the area function is given by this one. This is the graph of. And one easily observes that A derivative of x equal to f of x and A various choice of A index. This will turn out to be so I think these examples that we have looked at should give you a certain insight into the antiderivative of a given function. So essentially it suggests that it's actually the matter of computing the area between the graph of the function and the x-axis and the coordinates. Okay, so how to do this? This is the problem. Here we could do it easily because the type of functions that we have chosen are all linear functions on every segment. And the moment you go to a nonlinear function, for instance, something like y equal to x square, something on the interval 0 to 1. If you were to compute the area of this, first of all, unfortunately, this is neither a triangle nor a rectangle. Now you see, you cannot approximate it, or you cannot, subdivide this into sum of triangles and rectangles. Now that is the problem. So in that case, what do you do? The only process that you can follow is approximate. For instance, one of the ways in which you can approximate is choose several points here and then replace this by a polygonal curve which lies closer to the given curve. So it is something like this that you have the approximation is given by this. Now if you further subdivide, choose more points on this, you see that the polygonal curve will start hugging the given curve closely. So it approximates it better and so on. So you approximate it using polygonal curve. If you use polygonal curve, you know how to calculate the area. So the process is to get a sequence of approximations through polygonal curves or even using step functions. Now we will decide which is better. Step functions are easy to calculate because polygonal curves, again the triangles will come and give you some problem. Okay? So with this, so we have to approximate this possibly by step functions. Okay? A hint to this is this. Again, take the same function. Okay? What I do is I just give an approximation. This is the first step. This one I take an interval. This part I approximate. Now what I do is I approximate it more closely. What do I do? I introduce an additional point here, and then you see that I have this one, I have this one. Now you see that the new approximation takes care of more area under the curve. And then again you subdivide, and keep on, choosing step functions. the sequence of step functions which approximates to the given function, and then the area is also correspondingly converge to the area under the curve. Now this is our expectation. So that's what we are going to work with. Okay? So I think these examples have given you a lot of insight into what it is, how the antiderivative is connected with this. Now here what we are saying is, if you calculate the area function, fine. In all these cases we have verified that it is the antiderivative. Therefore we expect, even in the more general scenario, you will get the same kind of relationship to hold on, because we have looked at several examples, and that gives a lot of insight. If you are still not very convinced about it, you construct more examples and then do the computation. Okay? So that's the process. So this is how mathematics is built. Okay? So if you work on this, now these examples give you a wealth of insight into the ways of tackling this problem. So we will take it up further in the next few lectures. Thank you very much.